I'm going to talk about acceleration. We've got displacement, which is the change in position. And this is a graph of position versus time. Displacement would be the change from one time interval to another. And then we have velocity. And velocity, remember, is the displacement per unit time for the average velocity. But what we found was the velocity is the slope, the change in position per unit time. We could write that as delta t, but we don't typically do that in our class. So the velocity is the slope of the position time graph. And so if we see here, the slope is getting bigger and bigger and bigger. Then it starts getting smaller, 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 and then gets back down to zero. So this would be kind of like the velocity graph for that displacement time graph. The acceleration is the slope. I should say the value of the acceleration is the slope of the velocity time graph. So here you've got a positive slope. It's got a positive acceleration. Here you've got a negative slope. Really, there shouldn't be a discontinuity like that, but for that graph, it would look like this because then there's a negative value for the acceleration because there's a negative slope of the velocity. So the acceleration is the change in velocity per unit time. And in our class, it's really average acceleration, but we're just going to say acceleration because we're only ever going to deal with constant accelerations. It's the change in velocity per unit time. So it's how much the velocity changes every second. And if we think of the velocity being in meters per second, and this is how I'm going to write meters per second, the units are meters per second, and we divide by seconds, the unit of seconds, then the unit for acceleration ends up being, you could say meters per second per second. You could say something, velocity changed by 5 meters per second every second, meters per second per second. But we tend to write that as meters per second squared. Meters per second squared is the traditional unit, the happy unit for acceleration. So acceleration, change in velocity divided by time, and we measure it in meters per second squared. Now what I'd like to do is now talk about, let's break this equation down a little bit, okay? So if we look at that, delta V over T, we're going to introduce some new variables here for a regular and intensified physics. And the new variables are going to be a starting velocity and an ending velocity. So we talk about the acceleration over a certain time interval. Now we say the acceleration, again, delta V over T, but we're going to break that down. We're going to say at the very beginning of that time interval, the velocity was V initial, the starting, initial or starting, which we write as V with a little I, and at the end, V final velocity. And that delta V, the change in anything, is always going to be the last minus the first. I always talk about my age, my change in how much has my age changed since 2020. Well, we would take my current age minus my age in 2020 because that was the final minus the initial. If I did the initial minus the final, I'd get a negative age change. My age hasn't changed by -3 years since 2020. So it's always the final. Delta V is always the final, V final minus V initial. Just like in displacement, delta X, it was the final position minus the initial position. So that is what we would put in there. A equals delta V over T. So we can rewrite that as A equals VF minus VI over T. Change in velocity in meters per second every second gives you the acceleration in meters per second squared. It's a velocity change. So you can be going really fast and have zero acceleration because your velocity isn't changing. Or you could be going really slow and have a pretty big acceleration because the velocity is changing. It's getting faster or slower. Any change in velocity. And remember, velocity is a vector. If we drew it in 2 dimensions, we could have an arrow like that. So of an acceleration, this would be an acceleration if it went from this velocity to this velocity, okay? Or this could be an acceleration right there. If I went from this velocity to that velocity, it would be a negative acceleration in that direction. Or this could be an acceleration from there to there, because even though the magnitude is the same, the direction changed. So any change in velocity, we don't talk about this too much in our class, but it absolutely is an acceleration. So if we talk about driving a car, if you're driving a car, if you step on the gas, you push down on the gas, well, the magnitude of your velocity has changed. You hit the brakes, the magnitude of your velocity has changed. In other words, you get slower. It's really your speed that has changed. Or if you turn, the direction of your velocity has changed. Those are all accelerations. And acceleration is a vector. Sometimes we write it like this, indicating velocity is a vector and acceleration is a vector. This isn't the symbol for average, okay? But those are both vectors, and they have the same direction. The direction of the acceleration is the direction of the change of velocity. Okay, so let's figure out how we use this to solve problems. And what we want to do is we want to start a new process, which is called the solve method. Sketch, write the objective, list the variables, and find the equation. And the sketch is the most important thing. So let's say a car is going east at 20 meters per second. 3 seconds later, it's going east at 10 meters per second. Okay, so it starts going east at 20 meters per second, and over the next 3 seconds it slows down to 10 meters per second. So to figure out the acceleration, first thing I'm going to want you to do is pick a positive direction. That's east, I'm going to call that positive. You can pick any direction as positive as long as all our variables stay consistent with that. And then I list variables, okay? And this solve method I'll go into much more depth eventually. Sketch is the first part. Objective is what are we solving for? Well, I didn't even ask. Find acceleration. Okay? So the objective is to find the acceleration. You're going to see when we have more equations to deal with that actually writing this down is very useful. And then we list the variables. Sketch, objective, list variables. Okay, what variables do we have? At the very beginning, it's going 20 meters per second east. East is positive, so my initial velocity is 20. 3 seconds later, so the time is going to be 3 seconds. And then the final velocity is east at 10 meters per second. Vf equals 10 meters per second east. Then we can plug in these into the equation. So here's the equation. Vf minus Vi over t. There's another form I'm going to show you in a second. But the acceleration is going to be final 10 minus the initial 20 divided by 3. And that ends up being negative 3.3 repeating meters per second squared. Got to have our unit. What does that negative mean? It means it's accelerating in the negative direction. If you had an acceleration in the positive direction, it would end up going faster. Okay? Because if it's traveling in the positive direction and then you accelerate in the positive direction, the final velocity would have been faster. The fact that it's slower means it's got a negative acceleration. We can think it's hard to visualize it, an acceleration in the negative direction. But a negative acceleration, when you're traveling in that positive direction, will slow you down. Now, here's why it's really, really important to do this. Because we're going to have all sorts of different directions going on. If you don't have the directions right and the signs right, then you're not just going to get the wrong number, you're going to get the wrong everything. It's not going to be just plus or minus wrong. No, the numbers are going to be all screwed up. So you really need to be able to list this. Now, I mentioned another form of this equation is if we multiply both sides by t, let me make sure I've got ink, and we rearrange. And what we end up with is Vf equals Vi plus At. That's another form of that same equation. So, you know, depending on which one you're happy, this one's not on our equation sheet. This one is, but you have to know that delta V is the final minus the initial to figure out that equation. Or you're always given this equation on our equation sheet. We could have solved that the same way using the same thing, except I'm going to change one more problem because I want to make sure you have the flexibility and you understand how these things are going. Okay, so I'm going to have a ball going up a ramp, and later on it's going down the ramp. Okay, so the ball's going, I'm going to write it really quickly, hopefully. Ball's going up ramp, ball up ramp at 3 meters per second. The acceleration is, I need another pen because that's really getting lame. Acceleration is 2 meters per second squared down the ramp. After 4 seconds, what's the velocity? Okay, and once again, what we want to do is we want to sketch up the ramp. Here's my sketch. This is all I need for a sketch. Ball's going up the ramp. I'm going to call up positive. You could call down positive, but I just decided I'm going to call up positive. What's my objective? After 4 seconds, what's the velocity? That's a final velocity. Okay? Then I list my variables. Ball's going up the ramp at 3 meters per second. Acceleration is down the ramp after 4 seconds. So this is at the very beginning. VI is 3 in the positive direction. So every time you put a variable in there that's a vector, you've got to think about what direction. Is it positive or negative? Acceleration is 2 meters per second squared down the ramp. That means it's going to be a negative. After 4 seconds, t equals 4, what's the velocity? So what's that final velocity? This is kind of nice because this equation, I won't even have to rearrange it. I can absolutely use this equation, but here I go. VF is my objective. I just write that down, okay? That way I'll know when I've solved what I was solving for. VI is 3, A is -2, so plus -2 times 4. And so if 3 minus 8 is -5 meters per second. My final velocity is -5 meters per second. Another way to look at it, it was going up at 3 meters per second. It loses, if you think of it, it's losing 2 meters per second every second. So after 1 second, it would be 3 minus 2, 1 meter per second. After 2 seconds, it would be -1. After 3 seconds, -3. After 4 seconds, -5. That's a long way to go. These same equations will get it for you. Now, let me just say, what if you had screwed that up? What if you didn't put a positive direction and then you had all positive numbers for this? What you would have ended up with, and I'm going to write wrong way, wrong, is you would have said VF equals 3 plus A, and if you didn't have that sign right, 2 times 4, you end up with 11 meters per second. You had it going up a ramp, starting at 3 meters per second and getting faster, which just doesn't happen with ramps. So you can see that getting the signs here is extremely important. So to reiterate, acceleration is a change in velocity per unit time. We have one equation. This is kind of the definition. We could write it this way. Or this is in your equation sheet. You can always use this, even if you're not solving for VF. If you're solving for A, plug in numbers and use simple algebra to solve for A. So this equation will always work for you. But you really have to be very, very, very aware of what the directions are.